Hello and welcome back to Compiler Programming. Today I wanted to work a bit more on structs and to be more precise on types in general. Right now we have these built-in types which are signed and unsigned integers, right? So we have S32, S8, S16, U8 and so on and so forth. And we also have structs and we have arrays. So if I do, I think like this, that would be an array, although I'm not even sure it's supported inside structs. However, we are definitely missing support for sort of C-style row unions where same part of the struct is treated as different types. And I'm not exactly happy how it is done in C. So just for clarification, let's open up some file. I guess we can go to value definition and see how it's done here. So yeah, we have these union definition, right? And it can be any one of these types. And they are all located at this position in the struct. So we have operand type, which is S32, then we have U32 byte size. So that means that like we are at offset 8, we'll have any one of these things. And that is sort of fine for easy types, but it quickly falls apart for more complicated ones. So if I look at this one, for example, like this is already a bit hard to read in my view. And more than that, it's you have to use separate features which are not even standard to support partial fields, right? So we have a field here that is defined very weirdly. It's sort of a U8, but then it only takes up 4 bits inside of the type. And that's kind of, you know, first of all, it's a bit tricky to use. Like if you're not careful with bit fields, you'll end up with lots of headaches because of how C treats them. And also you have this combination of union, struct, and bit fields and whatever. And even all of that is not necessarily sufficient to describe all of the complexity of some layouts of memory. Like for example, here we simply just cannot say what is the size of the unwind code array, even though it is sort of known. It is this one, right? So they are tied together, but there is no way to specify that. So all in all, as soon as I start packing fields together, becomes really inconvenient in C to deal with that. So different languages solve this kind of differently. In Rust, the compiler doesn't even guarantee the layout of the struct. So you just say, okay, I have this struct and it is free to reorder the fields in it if it is better for compactness. So let's say I have another struct here. We have struct foo, and this struct, well, let's say this is an S8, and then S32, and then we have another S8. So in C, if we have something like that, then what will happen is we'll have a byte, then we have a kind of padding X, which is 3 bytes that is inserted by compiler. Then we would have S32 and then we have another S8. So all in all, and actually because we have S32 here, that means that the whole struct needs to be aligned to 4 bytes. That means that there's going to be another padding inserted here. So instead of like in total, we have almost half of our struct size wasted, which is obviously not great. But on the other hand, the layout is very strict and guaranteed, and X will always be on this position, Y will always be on this position, and Z will always be on this position. So this is known at compile time and doesn't change depending on how compiler wants to do. So this is like C does this. In Rust, for example, when you say that, what will end up happening probably, like there is no guarantee that it's exactly what's going to happen, but I imagine that this Y will be moved to the top, and then X and Z will be here. And then at the end of it, there will be only two paddings. So because we still need to align to 8 bytes, to 4 bytes, but we reordered these ones so they go one after each other, and now we only need to have one padding for the alignment to work out. Now in C, you also can have something that is like peg structs, which have different syntax between compilers, I believe. But the idea is it throws away the alignment and it just says, okay, that is like this. So we don't care that S32 should be aligned to 4 bytes because itself is 4 bytes, and we're just going to treat it like that. And this is more or less, this usually is done for things like file formats. So in our P32 code, if we actually look at, so I'm not going to jump in there, but if you look at the definition of something like image section header or something like this, you will see that all of them are defined to be packed. I think, yeah, optional header and so on. So all of these things are defined to be packed because they have to do with file formats. Now, this is sort of probably a lot of times this is what you would want on x86 because right now it seems that processors don't care about alignment that much, or on at least x86. I have no idea about ARM, need to investigate that, but I think the ARM does care about alignment a lot. But it still might be cheaper to just do this extra operation of fixing up the alignment than doing something else. But regardless, so this is the default thing in C. This is the packed version. This is what Rust does. It just rearranges the fields to minimize the padding at the bottom, but still has the padding. And then you have union support, and C and Rust, they both have the same union, which is what we saw here. All right, so you basically just define multiple things that are all in the same memory. And I think I didn't really see very different implementations of that. Maybe I wasn't looking hard enough. The only one I'm aware of for unions that is different is in unreleased Java language. And there, basically for unions, you can say something like, I think it looks like place X or something. I don't remember exactly the syntax, but the idea is before the field, you can say that it should actually be at the same location as the X field. And this seems more powerful to me. So I also want to go in something like this direction, but I'm not exactly happy with the syntax and how it's done. So here's what I'm thinking about, how I want to deal with all of this jazz. We have several things that we need to take care of. The first one is there is, if you're talking about types in memory, there is just a packed types that are certain size, right? So we have n bit sized types, something like S8, S16, and so on and so forth, right? This is what we have. Then we have n-sized array types. So we have, I'll actually change how I write this. So we'll say 64 as, or like 30 as 8, right? So we have 30 bytes. Oh, maybe I should keep the original, say 30. Um, so something like this, right? Then we have structs. And structs is a very, as you can see, it's a very poorly defined thing. It's very different thing in different languages. So it doesn't have a strict semantic to it. But the idea is that we have a type that is a collection of types at different bit offsets. And I say bit offsets and not byte offsets because of bit fields, which are often very useful. So here, this field is actually at offset 12, which is not divisible by bytes, right? And this is something that is a bit awkward in C to deal with, I believe, because C decided that all offsets are based on bytes, and this is going to be a difference with what I will be doing here. Anyway, so this is a collection of types, and this is going to be structs, unions, yeah, basically structs and unions. So this is what we have, and there is an extra one, which is null terminated types, which is also an interesting thing to think about. How would, like, can we somehow put that in type system as well, so our compiler knows that at the end of it there is a zero? And that's sort of an interesting side question. And I want to unify all of these to a certain degree and allow quite a bit of control with for the user of the language to decide how this all gonna work out. So here's the idea. We will have um, a generic keyword type, and I don't know if this is gonna stay like this. Maybe I will call it memory layout, maybe I'll call it something else. For now, let's just say it's a type, and it can come in different flavors. So the first flavor is, as what we saw, we can just say that's a type of 8 bits. And then obviously you can have something like 16, but in the same thing you can say B1, and this is a Boolean type of only 1 bit. Now, whether you will be able to allocate that separately or not, this will depend on something else, and this something else is now what we will talk about. Next one is the arrays, and arrays are, I think I will leave them as they are right now. So they are not really their own type. You can just say that, like you can basically write that, and this is an array. So I will leave it as is. But as far as structs go, they will also be just types. However, instead of providing a number here, that is the number of bits, you provide a special, for now I think they will be just keywords, but later on I also imagine they will be user provided functions that are called at compile time that will do the layout for the fields. So we would have something like type cstruct, and then if I write these things, right? So let me grab this. So basically, if I do type cstruct, then we'll end up with this layout, the same as what we have with cstructs. We would have type something like auto pack. I don't know if that's a good name for it, but basically For now, I'll call trust struct, and it will be doing this thing, right? So it will reorder the fields and do what you want. And then you can have packed one, which is exactly the same as the packed one in C. So these would be the types. They all look the same, and you can just provide whatever you want. Like for now, this will be hard coded, but then I want to make it so that you can provide whatever you want here and transition these keywords into something internal to the compiler, but it's also basically just a function that receives these fields and then decides where to put them in the struct and what to do about all of that. And now, as far as the unions go, so I'm going to go with something like this, and it will come in two flavors as well. So the first flavor is if we want to overlap two fields, we can just say, I don't know, y16 is at y, and the type of it is 16. Maybe, I don't know, I haven't decided what to put here. I'm not really thinking too hard about the syntax. It doesn't really matter what I put here. Maybe add is better. Maybe I will put, I don't know, something like just braces. I don't know. That doesn't really matter. The point is, we would have a way to say that this field is at the same location as this field, and the type of it is now S16. So this provides enough functionality for the union. The cool thing about this approach is I also can provide hard-coded values there. And I can say things that I would not be able to say in C basically at all, I think. Yeah, I don't think I could say something like this in C. And this is kind of interesting, right? So I'll say, I don't know, X whatever. That doesn't matter what the name of it is. The point is, I'm putting this field explicitly at offset of 4 bits. So it will overlap part of X here and overlap part of Y here. Now, the CPU doesn't actually have a way to address this field, but this is a separate topic altogether because we can we can generate basically getters and setters for this that are reasonable enough to something that the CPU can understand. Like it could be something like overlapping right or whatever, and deal with this. I'm not even sure that I will support it right now, but having this syntax at least theoretically means that I could do this, or we could decide that whatever you put here has to be what CPU can write to or something like this. There are a bunch of versions of how we can decide to deal with this, but as far as the syntax goes and functionality, it is definitely there, and I find these kind of nice. So this is the plan. Today, I'm not gonna do all of it, definitely. The plan probably will be to support just these to start with, and then slowly work towards other versions. So for today, let me take all of this stuff and maybe what I should do is I'll go to GitHub and I will create a new issue so I don't lose all of what I just spoke about, and more generic struct type definition. I will clean this up a bit later, but for now this is just gonna be dump of what I'm thinking about. And now we can jump into the coding itself. Oh, I haven't also talked about null termination, but it's fine. We will get back to that. Okay, so we have struct, and this is what I want to have. Let's switch this definition to be something else. So we say type C struct, right? And we might also have, yeah, so we have actually another test that deals with structs. So we also need to switch that one. So we say type C struct. Okay. So first of all, this is no longer struct definitions. This is gonna be, whoops. This is gonna be type definitions. Oops. Do you still build? Yes. Okay. And what it will do, okay, so we change this to word type, and then we need to match a parenthesized. Okay. And now we need to do a bit of a tricky match, maybe. We say if. So this is, how should I call this? Layout, maybe? So if layout children or layout token children is, well, let's extract this. So we say U64 layout children count is this. If layout children count is 0, then what do we do? Well, we go to error, and error will still do this. Maybe result, token value make. Value star token star replacement token is this. Actually, we move this up. I don't know, error is fine. So the idea here is if we came across, actually this is never gonna be 0, is it? Okay, it doesn't matter. The idea is that if we have type and it has nothing here, then there should be an error. Okay, and then we say to do printer. That is fine. Else, if maybe you should actually do a switch. So case 0 is this stuff, right? And then we have case 1. And here we can say token star token mm, whatever token is dynamic array get layout token children 0 if token type is token type ID. Okay, else evaluate. So let's say panic to do evaluate constant expression for bit size. And if it is ID, then we are in the, we might be in the struct territory. So we need to check the ID. If, so we can say slice type, layout type is token source. If layout or switch, might want to refactor this later. Layout type, actually I can't switch, so it will be if slice equal layout type slice literal cstruct else so we only support cstruct as a thing. Actually, now that I'm thinking about it, that's not exactly correct. So this should go into here. So if it is ID and it is a cstruct, then we deal with it specially. Otherwise, we will just try to resolve it as a constant and do something else. And ideally, later on, this will also be just a constant. It will be a function, and then we just compile time call this function. But for now, I will hard code it. Maybe let's add a comment saying that should be a compile time function later on. Okay. So this is good. And what do we do otherwise? So break. Actually, we can do maybe do a sneaky thing. We can say fall through. So basically, if it is a single item and it is this, then we do a special handling. Otherwise, we will not do a special handling. So here we say break. I think that should work. Okay, and we need to say something like bool is needs layout block, and here we say that it needs layout block. True. And now we can say that if needs layout block, then we need to do this, which is going to be a bit awkward. That is indeed very awkward. So let's do it manually. What this does is this, and then we can take this and put it over to here. And then I can say token star layout block is 0. If needs layout block, actually I can do it like this and move this over to here. That sounds reasonable to me. Here we can for now say that we have a layout block because we will panic otherwise anyway. And if we have a layout block, it was previously called body probably. Yeah, so this is the thing. Sounds good. Sounds fantastic. The rest of the stuff actually stays sort of the same way. What am I missing here? I am missing a brace. Okay, if I haven't messed up anywhere, this is all we need to do for the struct version. So let's see how that works out. Okay, that did not work out that well. I wonder why. So we didn't trip out on this session, we tripped out on something completely different. Let's open up the debugger and see what's going on. Okay, I don't need this stuff. Okay, where are you unhappy with? First of all, which test is this? So it is inside of here. And I assume it is unhappy with the point. Token array definitions, and if we look at name, yeah. So it is unhappy that it doesn't have a descriptor. Descriptor, yeah. Okay. So first of all, might make sense to be protective here. So that's what the first thing that we'll do, I guess. If not descriptor, actually, let's add this maybe right away so that we will have a failing test here. Error builder. Yep. I'm not sure if mesh type already reported it. But we can say that could not find type. And then we say return true or something. Or return false. Yeah, doesn't matter. Target token, no, that would be yeah, it's a bit tricky to get the right location. For now, I'll just say this. or define. Okay, so that fixes a problem, sort of, but there is still a question, why did it not match? So let's get back to our type definitions and verify that whatever we have here actually makes sense. We match on the ID. It must be a literal type. Then there must be a parenthesized expression. And then we do this dance with the sysstruct. Let's break there and see what is going on. That was the wrong place to break. Okay, so we managed to match on this. Which test is this? Yeah, this is the correct test, so that's great. We have, we should have one child. Yes, we do. We switch on that, we get into case 1. We get the child. The child is an identifier, and that identifier is a sysstruct. So we have layout block. That should also be fine. Did we get it? Layout block, yes, we did. And I think I know what's going on. Yeah, I definitely need to do something about this replacement. It's no longer working really well, but that's not a job for today. We can say, actually I can do it there, and say 64 replacement count is basically, if we have a layout block, then replacement count will be 3, otherwise it's 2. Now it should be better, I think. Let's see. So we go through this, so we go here, we get layout block, we get assertion, blah, blah, blah. We rewrite these stuff. We have fields, we can do stuff to them. We have 2 of them. Seems that we have quite a lot of fields. How many definitions do we get? 6. That's a lot. Oh, yeah. That's just because of semicolons. So we have empty ones here. Yeah, that's okay. The question is, did we get something into a struct descriptor? Descriptor type struct, fields, data. Well, we get 2 fields, so that's good. Seems fine. We get a type, we define the type. We get the replacement token, and then we get the replacement count, and we do the replacement. I mean, should be better. And indeed, it is much better. Okay, so let's commit that. So Ep125, start working, transitioning to new type definitions. Okay. What else can we do? Well, let's do a custom sort of integer type. I will not transition the actual types because they are sort of they are all over our code, and we will need to do many different things to make this work everywhere, but I want to have the basic one working. Maybe I will do it here. Should be able to parse fixed bit sized type definitions. And then let's take this, for example, as a test. And we could say int 8 is type 8. And then we actually need to use it. So we call it test. This will not get anything, it will not return anything. And the only thing it will do is it will create a value of that type. X is int 8. Actually, even that is a bit tricky because we will not know what to do with it in terms of stack allocation. So there are multiple problems. And the first problem is we'll have to now introduce a new operand type, kind of, and then we will also not know what to do about it in terms of stack reservations. But let's still do this and see what will happen. So we say valueless function, function type void to void test, and then we just do checker that we do not explode. So something like that. This test will panic, or actually it just fails. Oh, I guess because we cannot parse. That's interesting. I would expect it to assert over here with this panic, right? Because it says type 8. What is happening there? Let's try to run it in here. I'm kind of a bit curious. So we don't print out anything, but we also don't get this function. What if I comment this out? Is this any better? Oh, I know what the problem is. Yeah, there should be a semicolon here. Okay. And now we should get a panic. And indeed we do. Good. Good, good, good. This is what I wanted to have. Now we need to do the evaluation. So how do this happens? Constant, talking to write constant expression. It is here, definition, scope define lazy. uh, lazy um, lazy constant expression. Where are we actually forcing this? Rewrite constant expression. Yes. Value is the result. Token force value. Okay. So I think I want to take that, maybe. That's an interesting question. Okay, let's take this stuff and put it into here. Okay, we have token mature state and it wants to have children, so we will give it children. We'll say layout token children program state scope builder. This seems fine. Result. Okay. If not result. So this is an error version of this. Okay. We get the value. Rewrite constant. Okay. Let's see what happens if I do that. State has function parameter. Yes, that's fine. We'll call you layout state. Okay. So this will match it. We should not call this result. We should call this value layout bit size, or just bit size value. And we put here bit size value. Yeah, so we should have at least one of those. And now we will do different things depending on whether it is a bit size value or it is layout. So if bit size value, then we do something. Otherwise, we would do what we were doing before, which is this stuff. That sounds good. Result. Who allocates the result? You allocate the result. We would need result anyway. Then we can put it here. Like so. And we need to actually do something here. And that something is the following. We need to create a new descriptor, and this would be like a pack descriptor and a descriptor. So we need to have a new type, and that type is I will call it a pack for now. And a pack type will have a bit size, which is this stuff. So here we need to handle the actual size. We need to say if not is immediate uh, like operand is immediate. Yeah, is operand is immediate. Result operand. Then to do error, go to error. So we did a constant evaluation, and we need to verify that this is an integer and this is an immediate integer. Operand is immediate, and then if result uh, descriptor type is not descriptor type integer. This would be quite interesting what this will turn out to when we transition everything to be a pack, I guess. So it is interesting. But for now, like maybe I should just turn this into integers and treat it that way, but I'm not so sure. For now, let's keep it as a new effect type. Now I can say that we have user2 bit size is S64 to U32 of operand immediate as S64. That sounds great. Of result operand. And we have bit sized here. Yeah. So we get the pack descriptor. We don't do any of that stuff, but we do need to create a new list things. They are actually exactly the same as they are here, so we can do something better. We can say descriptor star type descriptor, or just descriptor, and move this allocation here, and then we will just do the following. This goes away, this goes away, we put this one here. So if it's a bit size value, we will create this a pack one, otherwise we will create a struct and do the parsing of fields, but regardless of which one it was, we need to create an actual value that we can then assign to that constant, right? So here we would, like this part of the statement creates a value, and then this value is assigned to point. And this is what this code does, sort of creates that value. But here we don't need to say descriptor, we just say descriptor. And that seems good. Well, that's about all we need to do here, I think. Right now, we just need to add this pack descriptor type, which does not exist at the moment. So let's shove it in here and see what breaks, because we will have it in multiple places. Bit size, not a member. Yes. So that's something for me to fix later on, because right now it is just byte size. And that's no good. Actually, it's not even part of it. So maybe it's fine. I can say, well, let's do it this way. Descriptor, descriptor. Where's integer? Or float one. Descriptor of pack. And here I would say bit size. And let's actually make it the U64. Descriptor pack. Pack. And then here it will be to U64. So we just need to know that it's not negative. That would be awkward. And, and then we say peg bit size is bit size. Yep. Okay. Now we have to fix all the different places instead where we had different types. What is this thing? Compile time inval. No idea what I'm gonna do here. Not even gonna think about it for now. What are other places where we have it? Same here. There is definitely no peg types in C in this sense. This is descriptor byte size. Hmm. This is kind of tricky. So we need to round it up. Whatever is the bit size, I guess that would be the easiest way to deal with this for now. So with a type pack, we would say pack bit size divided by 8. I always forget how to round an integer correctly. Integer divide round. Rounding integers, yay. Okay, so this is what we want. So we do plus 8 minus 1 divided by 8. Yeah, makes sense. Makes sense. I can do actually whatever. U64 size of byte is 8. And then U64 to U32. Okay, that sounds good. Same type. I think it should do whatever the struct was doing. Yeah, so this should be like this. Also, tagged union will go away eventually, and it will be done differently. And struct will also go away, so hopefully all of these will collapse into one later on. Okay. I think now it should be fine. It will compile, I hope, and we will be good to go. Well, apparently no. Apparently it will crash. Let's see why you're crashing. Result descriptor type. Yeah, that's definitely wrong. That should be something totally different. It should not be result, it should be bit size value. And here as well. Okay, let's try that again. Great. Cool. So this is basically what I wanted to do for today. Obviously, there is a lot of work here still left. I will need to, or I would want to, at least transition sign types somehow to this form as well. I mean, not sign types, but like integer types. But this is going to be a bit tricky because right now a lot of things are hard coded in the compiler itself. Like it knows a bunch of stuff about integers and how to deal with them, and that's not how I want to for it to be long term, but that it is how it is today. So the first part is transitioning this struct, and the reason I wanted to do that is because then it will allow me to start to slowly do the rest of the stuff. So we had this already generated compiler types, but I could not generate unions here, and I needed a way to generate unions, so now I will be working on that. Now that I'm thinking about it, since we do need unions, maybe I will need to also change this setup here. So this is what will be inside of token match struct field. We'll have to do something a bit different here. I will not probably do it today. That will be either a follow-up video or I will do it offline. But basically in here, I would add support for this stuff, right? What we discussed, that I can place it at a particular location that is another field. But for today, that would be all. Thank you very much for watching and hopefully see you next time.